query language that looks a lot like SQL. And so they've changed the term. It's now often used to be, instead of there's no SQL involved, to be not only SQL. But the interesting thing that's come out of this is that there are actually some useful data storage and retrieval techniques that have been built into some of these SQL products. And the thing about SQL is that it actually specifies the queries, it doesn't specify how to get the data. And so if you start thinking about an interface where above it you're specifying a query and below it magic happens and all the physical stuff happens, well, you can tie that onto any physical data storage mechanism that you can come up with and take advantage of it. And that's one of the things that's happening in the industry at this point. You'll see the term sharding. This just means you take your data and you break it into a bunch of little pieces and scatter it across a lot of things. But the complication, and I'll talk about scaling out in a moment, the complication is that once you scatter your data all over the place, you need to somehow query it. And that leads to techniques like MapReduce. And essentially MapReduce is a patented algorithm. You really ought to go look up the algorithm that's in the patent. Because essentially it says is that there's a user-defined, the patent says a user-defined algorithm for partitioning the query on multiple nodes and a user-defined algorithm for integrating the results. Originally, when people were talking about MapReduce, the developer who was doing the query had to go off and do all of the work to figure out how to distribute the query and how to integrate the results. In newer implementations, the operations to do the distribution and the integration are generated by the database software rather than having the developer do it. And I believe that's the correct mechanism. Schemaless. A lot of data projects haven't wanted to take the time up front to do design. We don't have time to do any stinking design. We've got to get the application up and working. Have you ever heard that? We don't have stinking design time to design this 100-story skyscraper we've got to start building. Is that going to work? What happens with schemaless is that the schema information still exists. It's just that it's embedded in the data, or it's embedded in the code that supports the application, or it's on some developer's wall. Essentially what the schemaless database movement is doing is reinventing databases from the 1960s. New SQL. You guys remember Coke and then New Coke and Coke Classic? Well, what New SQL is really doing is it's giving you everything that you had with SQL databases, but layering it on top of some of the new storage techniques, giving you full support for ACID transactions, etc. So giving you all of the new things with all of the old things. So I'm thinking that we should start talking about SQL as being SQL Classic. I haven't convinced anybody of that yet. So I want to take a high-level view and talk about data types and storage models and data distribution and access and so on. So we've got the traditional data types of character and numerical and date-time timestamps and large objects. And we have some of the newer big data types, multi-dimensional arrays that you've probably heard Peter talk about if you've been around them at all. Images and videos, documents, sort of loosely formatted data, objects. In the 1990s, object databases were going to replace SQL databases. Spatial data. Is spatial data a big data type? Probably. So you spatial guys have been doing big data since before big data was invented. You got the data storage models. How the data actually sits is represented out on the disk. SQL databases typically have been row store. You store tables where you store a row at a time. There are implementations to do column store, where instead of storing a row together, you store the columns together. And that has some real benefits if you're only going to be accessing a subset of the columns. If you're doing a select star on a columnar database, it's not going to work well, because then you have to go off and get all of the columns anyhow. We've got key value stores and document stores, like XML and JSON and Bison, graph stores and multi-dimensional arrays and objects and whatever. The point is that you've got all sorts of different ways of representing the data. And while a lot of this has been associated with NoSQL or big data implementations, it's just another way of storing the data. And if we can abstract that a little more and layer some common interfaces on it, then I think we'll go a lot farther than if we have a specialized interface for every specialized data type. When is data stored, accessed? Sometimes it's accessed after it's stored, sometimes it's accessed before it's stored, or maybe even instead of. And I actually had this slide in long before I knew what Jeff was going to talk about. Honest. Data distribution. You can have a single node, and what you do is you just make that node bigger and faster with more disks and more CPUs, or you can cluster things, or you can replicate things, or you can do what's called horizontal distribution, where you spread it across multiple computers. With vertical scaling, basically when you need more compute power, you buy a bigger computer. So you get more CPUs and faster CPUs and more memory. And there are some arguments for vertical scaling, and in fact, there are a lot of applications in the world that will scale vertically quite nicely, because we're now seeing 22 or 24 cores on a CPU chip. You know, you put 2 of those in a server, or 4 of those in a server, and you've got a fair amount of compute power. You know, maybe a couple terabytes of main memory. Storage capacity. Samsung is shipping, if you're willing to pay the price, a 15.3 terabyte solid state disk in a 2.5-inch package. And for next year, there are a couple of announcements that came out in August of like 30 or 40 or 60 terabyte solid state disks. So 10 years ago, you had to scatter things across multiple systems to get that kind of storage space. In the next couple of years, you're going to be able to put, you know, a petabyte or a couple of petabytes in a couple of rack units in your computer center, and any small company will be able to afford it. Which means we need to build the techniques so that everybody can take advantage of them. The real bottleneck is going to be networks. I mean, they're now 20 gigabit network adapters, but if you're storing a couple of petabytes, you still don't want to move it around because 20 gigabits is not that fast. So not all problems can be solved with vertical scaling. And you have all the potential problems. What if things break? What if the data center breaks? You ever had a data center break? It can get pretty ugly. So what people are doing is scaling things out across multiple servers and potentially across multiple data centers. I don't have a graphic artist, so this is a fairly simple diagram, but the idea is that we spread things across multiple computers with their disk subsystems, and somehow we have to manage it and put it back together. And of course, when you start spreading things out, you've got multiple points of failure, so you need to have redundancy, which is good, but it adds additional levels of complication. So let's think about horizontal distribution. In some ways, a single server is the simplest case of horizontal distribution. It's the line with one point. Or maybe you have a cluster or multiple clusters in the data center, or multiple data centers on a continent. Big problems have multiple continents in the world. But I don't want to think small. Let's spread our data centers across multiple planets in the solar system, or multiple solar systems in the galaxy. I don't think I need to worry about multiple universes, but when we start working on that level of things, there are going to be some challenges around network latency. But We need to think in terms of, let's think big. None of this small stuff with just a couple hundred computers, let's think really big. And then you need to distribute the processing, and that's where the MapReduce type algorithms come in. So that you transmit the results, not the entire data set. But that's all fun and games. Distributing data across multiple data centers there's some challenging problems there. But in a lot of ways, that's a simple problem. The complex problem, and a number of speakers have talked about this, is integrating data from multiple data sources. How do you discover that data exists, where the data actually, in a network sense, exists? What the access methods are that are available for it? How do you understand what data is available and what it means, what the security and privacy requirements are? And a lot of you work in government organizations where basically you're required to make the data available. But there may actually be organizations that have data available that is useful where they want to make money off of it. So there are going to be some business details to be worked out. And what are the possible operations that are available on a particular environment? How do you integrate the results? I think there's some challenging problems in this area. So my diagram of integrating multiple data sources is this. It looks kind of familiar. I just sort of scaled it out and added more things. And I have this theory that you need some sort of mechanism to be able to say, hey, this is the data that I have available, this is what it consists of, and I'm calling that a data source registry. And so what I need to be able to do is to have my analytics engine go off and identify data sources that are interesting by looking at the data source registries and partition queries and get results back and somehow integrate those results. And I kind of think this is going to be the hard problem that we need to work on over the next couple of years. Because there's going to be a variety of data representations. And it makes sense that there are multiple data models to handle the data diversity. One of the store everything now and figure it out later is what happens with a lot of JSON type data. I want to define it up front, I want to just store it, and then I'll analyze it later. There's actually room for that, although it often gets misused. Now, I talked to somebody a couple years ago who described this model as puke in a bucket and filter out the big chunks later. Which is kind of a vivid picture, but I think has some validity. There's going to be a variety of data source ownership. Stuff that's owned within your own organization, stuff that is publicly available, data for hire, or some sort of derived data. And I'm probably don't have a complete list there. But the point is that there are going to be business details that need to be worked out. And so the data source registry requirements are that we need to be able to have a mechanism for registering data. We need to be able to have a mechanism for understanding what data is available, supporting discovery, a mechanism for understanding the semantics of the data. So all that schemaless stuff, to actually make data available in a general way so that somebody else can figure it out and understand it, you really have to have all of that schema information registered someplace so that somebody can look at it. So they understand what the data is, what's comparable, what the provenance is, where the data came from, what the likelihood is that it actually is valid data. And there might be some costs involved with accessing it, use restrictions or service level agreements. One of this year's buzzwords is something called blockchaining, and they actually have some usefulness in doing this kind of automated business agreement. And as a standards guy, I'm going to claim that standards are going to support this kind of integration. We've got query languages. A lot of the interface to databases is done through JDBC or through things like Sparkle or XQuery or product-specific APIs, or SQL. You probably all associate SQL with tables and columns, rows and columns, but over the last, I don't know, decade, 2 decades, we've expanded SQL to support XML. We've added support for JSON, JavaScript object notation. We've added support for polymorphic table functions, which I could talk about for longer than I actually understand. And we're adding support for multidimensional arrays, which Peter can talk about in great detail. So the point here is that there are all sorts of query languages, but there is work going on to integrate a lot of capabilities of this kind of access into SQL. And actually, the next topic that we're looking at after this is streaming data. There's data analysis and visualization. How do we integrate things like the R statistical package and other statistical packages? One of the things about the big data ecosystem